Yeah, I welcome you all for another beautiful presentation on our control system subject. In today's presentation, I would like to explain you about the phase lag network or otherwise the phase lag compensator. This is widely used compensator circuit in control system subject or in control in industrial applications. Wherever the control system concept is there we will use this phase lag network or phase lag compensator. So the main application of this circuit is it improves the steady state response, and moreover this will be more effective at low frequency signals. So let us see the basic circuit diagram of a lag network or compensator as well as its transfer function. Let us go into the subject. We will see its transfer function. Okay. In today's presentation, I would like to explain you about the phase lag network, which is the topic that I am going to explain you in this presentation. This is from control systems subject, and so far we have covered 51 presentations or lectures based on this control system subjects is concerned, and this is the lecture number 52, in which just I am going to explain you about the phase lag network or otherwise also called as phase lag compensator. So we are discussing about the compensator circuit which are widely used in control systems applications, and as we have discussed in our previous presentations, if you refer in industrial applications, these compensators are required in order to improve the steady state response of the control system, right? So in this way, this phase lag compensator or phase lag network is also very important, and basically it offers a very high gain at lower frequencies. That is, this is one of the very important aspect of this phase lag network. It offers high gain at lower frequencies. That's why this phase lag network can be acts as a low pass filter. So I will explain you. Let us see the circuit diagram how the phase lag network looks like, and we will see in this presentation the basic circuit diagram of a phase lag network as well as how the transfer function is looks like. The basic circuit diagram is like this. It has a resistor, and then this is a simple RC network. If you see, let us call it as, let us say R1, this is R2, and this is the C, right? So this is your input Vi of t. Normally you can call it as plus and then minus, and this is what your output, this is V naught of t. Let us consider this is the simple RC circuit which is to be considered as a lag compensator circuit or a simply lag circuit. Let us imagine that the loop current I of t is flowing through this circuit, for example. Okay, so this is the basic simple circuit of phase lag, and for this we need to find out what is the transfer function of this network. What is the transfer function, that is V naught of S by Vi of S. What could be the expression for this? Let us see in this today's presentation the ratio of V naught of S by Vi of S, and we will see little more details in our subsequent presentations, right? So in order to derive this particular expression, let us see that, consider it as a loop 1. So for this, if you apply the KVL for the loop 1, let us apply the loop 1, okay? By applying, okay, by applying KVL to the loop 1. So if you apply the KVL for this loop 1, what it will be? It is Vi of t is equal to, tell me, R1 into I of t, it is R1 into I of t plus, and then R2 into again I of t plus, it is 1 by c integral of I of t dt. Call it as equation number 1. Clear? So this is what my first loop actually. For this I am applying Kirchhoff voltage law, that is KVL. Then Vi of t is equal to R1 into I of t plus R2 into I of t plus 1 by c. And similarly you can take the expression for V naught of t also. Output is nothing but this is the voltage across these particular terminals. Okay, that is nothing but you can V naught of t is nothing but the voltage across this branch, means R2 and C, or otherwise simply this V naught is nothing but voltage appears at this node. Okay, so this V naught of t can also be written as V naught of t is equal to, tell me, it is again R2 into I of t, because same current flows through it, and it is 1 by c integral of I of t into dt. Clear? This is equation number 2. And now apply the Laplace transformation to these both expressions and bring the ratio of V naught of s by Vi of s. I will erase the circuit and then I will apply the Laplace transformations. So after application of the Laplace transformation to these both expressions, then your V naught of I becomes as what? Vi of s. Clear? Vi of s is equal to R1 is as it is, it will be R1 only. It is I of s. I of t becomes I of s, and here again R2 will be the same. Your I of t becomes again I of s here plus 1 by c. As you have one integration, then one s will becomes numerator. This is I of s. Is it not? If you further simplify here, take I of s as common in this particular expression and call it as equation number 3. Right. So for the first expression, for the equation number 1, I am applying the Laplace transformation, then it becomes like this, the equation number 3, and from here I am taking I of s as common. Here it becomes, it is R1 plus R2 plus 1 by s into c. Clear? This is what my Vi of s now, and you can further call it as equation number 4, nothing wrong in that. And similarly apply the Laplace transformation to equation number 2, and then you write what will be the expression. So if you apply the Laplace transformation to the equation number 2, then it becomes, from equation number 2, it becomes like this. It is V naught of s is equal to, and simply it is R2 into, again it is I of s plus 1 by s into c, same as above, s into c, it is I of s. Clear? You can call it as equation number 5 if you require. Then take again I of s as common here. Clear? So from this fifth equation, you can write I of s as common. Then what you will get actually? Here you will get R2 plus 1 by s into c. Right? This is what equation number 6 now. This is final expression of V naught of s. Now, so from the output expression, consider equation number 6, and whereas from Vi, consider the equation number 4. So now, by considering equation number 4 and then equation number 6, take the ratio simply V naught of s by V of s. V naught of s by Vi of s, that is what our desired transfer function. Then if you take that ratio, means V naught of s by Vi of s, means equation 6 by equation 4. Then what you will get here? And definitely if you equate these two, definitely V naught of s by what you will get? I will erase this expression for you and I will write that. Right. So which is nothing but V naught of s by Phi of s is equal to, what is this? I of s by, obviously in both expression I of s is there, both will be cancelled out. right? V naught of s by Vi of s means this total quantity by this quantity. I of s is there, therefore it will be cancelled out. Then numerator it will be R2 plus 1 by s into c will be there in numerator, whereas denominator you will have R1 plus R2 plus 1 by SC. Clear? This is what you will get. And further, this can also be simplified as like this. And from there, what you will get actually? So, from there, this implies V naught of s by Vi of s is equal to, from there, you can write that, what you can write? You can simply take the LCM there, then it becomes R2 into S into C plus 1 will be there. R2 into SC plus 1 by SC, it by SC will be there. Clear? And by whole by, again you take this, what you will get? R1 SC, or otherwise simply SC into, you can write like this also, SC into R1 plus R2 plus 1 by SC, means definitely, is it not? This is what, after simplification, then this SC will be cancelled out, then you will get here R2 S into C, okay, plus 1, clear, by what you will get here, SC into R1 plus R2, okay, plus 1, clear. This is what you will get, is it not? And furthermore, if you solve for, this is what your expression, and further this can also be simplified as, this is what your V naught of s by Vi of s, clear. This is whatever, and further that can also be simplified as, and V naught of s by Vi of s is equal to, what you can, C into R2, you can take C into R2 or R2 into C, nothing wrong in that. R2 into C, if you take common, then what you will get there, S will be there by 1 by R2 into C will be there. Clear? Here I am taking as R2 into C as common in numerator part. Then only S will be there, S plus 1 by R2 into C. Similarly, what you will take common? C into R1 plus R2 you take as common. In denominator part C into R1 plus R2 take as common, then you will get S plus 1 by, S will be there, 1 by S plus, what will be there, C into R1 plus R2 will be there. Clear? This is what? Clear? This is what the thing basically. Then what you will get here actually after this, and further if you simplify this, definitely further this can be simplified as, actually in both the things, if you see, this C and this C will be cancelled out, and furthermore this can be written as R2 by, right, R1 plus R2. Clear? This entire thing I can put in a bracket actually, is it not? R2 by R1 plus R2. Then the remaining part I can write like this, S plus 1 by tau, let us say, S plus 1 by tau, where tau is R2 into C, R2 into C is the time constant, R2 into C, by S plus 1 by C into R1 plus R2. Clear? And again, and furthermore, if you do a small simple adjustment there, if you do a small simple adjustment there, here further you can write there this 1 by, if you take this R2 by R1 plus R2 in a denominator part, then you can write that S plus, this is V naught of S by Vi of S is equal to, I can write it as 1 by some constant beta. I can write as 1 by beta. 1 by beta is nothing but, I will take the beta as something like this, R1 plus R2 by R2. For simplification, I will consider beta as this, R1 plus R2 by, okay, R1 plus R2 by R2. So then if we consider this as beta, then this will be considered as 1 by beta basically. Then it will comes as S plus 1 by tau by S plus 1 by beta into tau. This is the simple expression you can write. Here if you take the small adjustment actually, again you can take some, if required, R2 as common as, if you take C into R2, R2 you take as common here, then it becomes as 1 plus R1 by R2. Again if you take small adjustment, here you will get the beta factor, okay, and finally you can have the transfer function in this form actually, V naught of S by, okay, V naught of S by Vi of S is equal to 1 by beta. This is what your final, I mean, transfer function for form of your phase lag network, where beta is equal to this R1 plus R2 by R2 basically. Is it not clear? So this is what the transfer function basically, 1 by beta into S plus 1 by tau by S plus 1 into beta tau here. So this is what, if you consider here actually, this is what S plus 1 tau is the 0, as well as S plus 1 by beta Z considers the pole. This is the 0, this is the pole. Therefore, S plus 1 by tau equal to 0. Therefore, S is equal to minus 1 by tau is the 0. So, at S value of this, it has 1 0, as well as at S is equal to minus 1 by beta Z, beta tau, sorry. So, this at this S value, it has pole. This is 0 actually, this is pole. Okay, this is what the thing basically. So here this is what the basic transfer function of this circuit, okay, and so the main advantage of this particular is that by introducing of this lag network in any control system, it improves or increases the steady state response of the system, and as I have explained just now, it offers high gain basically at lower frequencies. That's why it acts as a low pass filter circuits, right? So this is what the simple transfer function of a lag compensator or lag network, right? So this is what the beta, and in so let us we finish off here, and we will continue with the more details in our subsequent presentations. Okay, so I think you understood this to find out the transfer function and how the the network looks like. So in the subsequent presentations, we will see some more detail, and the rest of the network is the lead lag compensator. That also we will see in the next presentation, right? So thanks for watching, and we'll meet in the next presentation. See you. Have a wonderful day.